Hey everyone, today I'm going to be solving question 863, all nodes, distance k in a binary tree. So, how I'm thinking of approaching this question is pretty much that whenever I see distance k in a binary tree, when I start to see distances when it comes to trees and graphs, I start to think of a breadth first search, because breadth first search is a way to find like all the things like a certain distance away from a specific point in the tree or a graph. So if I want to, so one sec, getting spammed. What the heck is this? It's kind of annoying. Bunch of messages. Oh shoot. So this is how I do it. So we're we're told that we want to get all nodes distance k in a binary tree, and we're given the root of a binary tree. The value of a target is a, so we have to find the target, and then an integer k, return an array where all the nodes have a distance k from the target. You could put the answer in any order. All nodes are unique. A number of nodes. Target is the value of one of the nodes in a tree. Cool. Those are the constraints. So pretty much, like I said, when I start thinking of when I see like k distance, I start to think of like a breadth first search, because usually in when it comes to a tree or a graph, let's just even just convert this to a graph. If we think of all these edges as like edges that go front and back, I know this is implemented as a tree, so we don't really get that, but it's pretty easy to convert this any tree to a graph. To 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 do a breadth first search, like if you do a breadth first search, you can easily get all the elements that are k distance. For example, if we could do like a level order traversal. So if we want to get the one, right? We get the one. Like breadth first search explores like all of the neighbors first, all the direct neighbors first before it moves on to like the neighbors right after that. So it would look at these ones first, right? And it'll know that there's a depth of 0 there, or that's only one away, sorry. And then as we keep doing the breadth first search, like say these have a depth of 1, right? And then when we like pop the neighbors of like when we visit them, we'll pop the neighbors into our queue. So what yeah, when we pop the neighbors in the queue, we pretty much say that the neighbors are our depth plus 1. So when we visit 2, we'll look at the neighbors and we'll see 7, and then we'll put in our queue that 7 has a depth of 2 and 4 has a depth of 2. And then when we visit 3, we look at this one. It has like it's already been visited, so we don't pop that into our queue. But then we see 1 hasn't visited, so that one has a depth of 2, right? And if you wanted to expand, like if you wanted to have this running, pretend the k distance was 3, pretty much. Then when we visit this, we look at the neighbors. We pop 0 into the queue, and we say that that has a depth of 3. Then we pop 8 into the queue because that has a depth of 3, because that's a neighbor of 2. And then we would just return all the ones with like a specific depth, right? We could probably like early exit after we hit a specific depth, because we know any of neighbors of these ones are gonna be like one, like depth plus 1. So that's going to be like we don't even need to explore like any of these paths if they exist. So yeah, that's kind of like how I'm thinking of doing like a depth first search. That's pretty much why I think of a depth first search there. If because all these ones pretty much have a weight of 1, you could pretty much do depth first search always to find the shortest path when the weights of the edges are size 1. But if the edges had weights like 2, 3, 4, 5, like you'd have to use like a different algorithm, probably like Dijkstra's, in order to find like nodes that are like a certain distance away. And that's like a different LeetCode question. It's probably harder than this. So, like I mentioned, since we're using a binary tree here, we'll want to somehow convert it, like be able to convert it into a graph. So since it's a binary tree, all of each node kind of has pointers to the left and right children, right? So if I store the parent, so if I when I do a traversal, I store the parent node. I essentially convert it into a graph, right? Now we have bidirectional. Now pretty much given every single node that we go from, we can like traverse to any other node. So pretend we want to get distance that is like k from like this zeroth node, and say k equals 4, right? Now we'll do a BFS. Um, we'll say this one has a depth of 0, or like a distance of 0 because it's itself. But then we'll pop the neighbors into the queue, right? So we'll pop 1, we'll pop 8, and then we'll, like the neighbors are gonna have a depth plus 1, right? Or sorry, 8 is not even a neighbor. What am I saying? Only 1 is a neighbor, but it has a depth plus 1. So we'll pretty much put into our queue this one like 1, and it has a depth of 1, right? And now we visit this. Now when we visit this one, um, we pop its neighbors. So its neighbors are pretty much 3 and 8. So we'll say 3 has a depth of 2 because this one has a depth of 1. And then 8 has a depth of 2 because it's like 1 plus 2 here, right? And now you can see like how I'm like actually assigning depths to here. And now I process that. And now like let's do one more iteration. We're looking at 3 now. So 3's neighbor is 5, and it has a depth of our depth plus, or the depth of 3, which is 2 plus 1, which is ends up actually being 3 as well. And then you can see like how that equals 3, and you'll see that pretty much 1 2, yeah, 8 doesn't even have neighbors, so we're good with that. Then finally, when we have 5 and 3, we pop its neighbors into the queue, and we give it a depth of 4, and kind of we'll know to return that. That's kind of the insight, like convert it into a graph, find the specific node, and then like just do a breadth first search. Let's just get straight into this. What I'm gonna do is I'm gonna find that specific node by doing a breadth first search or a depth first search. Or basically, I'll store like parents. I'll store a set of parents, which is a dictionary, that's gonna contain all the backlinks. Then I'm gonna do like a depth first search. Then what I'm gonna do is like I'm also gonna get like parents. Then I'll say pretty much when I do the depth first search, I'll just do a pre-order. So I'll analyze a specific node, and I'll put its left and right children, and I'll assign me as its parents. So I'll say like if node dot left is not none, then I'll say parents of node dot left equals me. Say parent. Oh yeah. Then I'll do the same thing for the right. So I'll say right. So if the node dot right is not none, so I'm essentially saying I'm the parent of the left, and I'm assigning me as the parent of the right. And then what I'll do as well is I'll like just recursively call this. Do the same thing on the right. So that should build up our parent nodes. Then we'll just return. Right. That builds us like our specific graph. And now what we're gonna do is just like a simple breadth first search. So what we're gonna do is we're gonna have result here. Then we're gonna return the result. For breadth first search, we want to use DQ. So from collections, right? Then we'll say while the length of we'll initialize the queue. Say while, and then we'll start it off with like the target, and then we'll start it off with a depth of 0, because this one is at the specific depth. I'll say while there's items in the queue, we're gonna get the depth, and then we're gonna get like the actual, or we're gonna get like the node, and then we're gonna get the depth by queue dot pop left. We're grabbing from the front of the queue, so we're using a first in first out to do depth first search. Then what else do we do? Do we return the nodes or the values? Okay, we return the values. So we'll just say if depth equals, if the depth equals k, then we result.append node.val. Right. And then since we turned this into a graph, we're gonna need a scene array, a scene set. So we're gonna say target because we already seen that like we don't want to like end up in an infinite loop. So we say if depth equals k, result.append the node.value. When I do all these LeetCode questions, I do them like completely from scratch. So I want you to see like my thought process on how I actually solve all of these questions. So if the depth equals to k, we append that value, and then we're gonna actually add these elements. Like we're gonna add the neighbors. I mean, if the depth is equal to k, we don't want to even continue any further on that one. So what we're gonna do is like we're gonna have an else statements. Depth is not equal to k. If depth equals, so the depth is actually less than k here. So what we're gonna do is if the depth is less than k, what we're going to do is we're gonna pop the neighbors in. So we're gonna say we're gonna look at the parent. So I'm gonna be like the neighbors is pretty much equal to gonna be equal to like parent of the node node dot left and node dot right. These are the neighbors. Then for neighbor in neighbors, if the neighbor is none, continue. If we're doing some checks, if the neighbor is in scene, continue. Otherwise, what we're going to do is we're going to add scene.add neighbor.value because we know these are unique, and then we're gonna just add it to the queue here. I'm gonna say, what's the target, or what's the left of target? So the target is okay. So we start at the target. What we're gonna do is we're gonna queue.append the neighbor, and then we're gonna add in the depth +1. Run that. Valid syntax. What's happening here? Where's parent? Parent? Okay, because one doesn't have a parent. We'll do misspelling. What happened here? We got 7-4. We're missing 1. If the depth equals k, turn this. Okay, we're getting 7-4, but we're missing 1. So let's just print the length of the queue every time. Or let's actually just print the queue every time and debug that. Ooh, that's rough. Debug it a little bit. Why did we need that? Why didn't we get 1? So we moved 5. Did we move 6, 2? Oh, shoot. Wait. Why don't we have a parent here? Oh, sorry. I didn't actually call my self dot. Root. There you go. We didn't build our parents array. So that's how you solve this question. A little bit tricky. I didn't think it'd actually be that tricky when I first looked at it, but the implementation was decently difficult. Yeah. So just do a DFS to build the graph. Then now when you convert it into a graph problem, what you need to do is you could just do a breadth first search because you know breadth first search is going to like lead you this like the shortest path. It's gonna tell you like the shortest path to all the other nodes, and then that will tell you like basically the distance is the shortest path between it and a target node. So this is a distance of 2 from 5, and because like that's the shortest path between these two, so that's kind of why I use BFS there. I think I gave a better explanation at the start, but I'm blanking out because I've been on this for like 30 minutes now. So hope you learned something. See y'all in the next video.